we discuss about some topics in three-phase systems. So in these three-phase circuits, we have to, in this last class we discuss about what is three-phase circuits, what are the advantages of three-phase circuit compared to the single-phase circuit, how the generation of the three-phase voltages will be obtained. So under that we see about some of the advantages, that are the amount of conducting plate is required less for transmitting same power over a same distance under same power loss. And three-phase motors produce uniform torque, whereas torque produced by single-phase motor is pulsating. And three-phase motors are self-starting, whereas single-phase motors are not self-starting. And how this generation of the three-phase voltage will be developed means, for the same, when you take of the single-phase voltages, there is only one conductor will be placed across the poles. So whenever conductor cuts the flux lines, the EMF will be induced. That will be equal to EM sin omega t. In these three-phase systems, there is three conductors, three windings must be there placed. That is starting will be A dash, B dash, and C dash, and the three phases are R, Y, B, or A, B, C, whatever you have to represent. But here, when the three-phase system will be, so when it will be produces the three-phase voltages, so whatever the voltage and the phase 1 and phase 2, phase 3 must be, the magnitude must be same, and the phase angle will be 120 degrees phase difference with each phase. Then only it will be, the circuit will be the balanced circuit. Otherwise it will be unbalanced system. The voltage will be same and the phase angle, that means the magnitude will be same and the phase angle will be 120 degrees phase difference. So for the three phases R, Y, B, the phase angle will be 120 degrees from each phases. So for this we have to represent for the three phases, ER is equal to EM sin omega t, and EY is equal to EM sin omega t minus 120, and EB is equal to EM sin omega t plus 120 degrees, or EM sin EB is equal to EM sin omega t minus 120 degrees. So here, so the three-phase systems, the voltage and the magnitude, whatever the magnitude, that is EM in the three phases must be same, and the phase angle will be 120 degrees from each phase. So for the rectangular form, vectorical form, it will be represent as ER is equal to E at an angle of 0, and EY is equal to E at an angle of minus 120, and EB is equal to E at an angle of plus 120. And next thing, that is balanced. So when the three phases must be in the form of the same magnitude and phase angle will be 120 degrees phase difference, then it will be, the system will be balanced. So otherwise it will be unbalanced system. That means the three phases, the magnitudes or voltage, whatever in one form it will be not equal, then it is called as unbalanced system. So balanced load means when the impedance, whatever the impedance must be there, that will be in the form of three phases must be same. That means in the one phase it will be 2 plus J3. So EY will be also 2 plus J3. BY or YB also 2 plus J3. If suppose it is one is 2 plus J3 and the other is 3 minus J3, like that it will be there, then it is called as unbalanced load. Balanced load and unbalanced load. So next thing we discuss about the if the total, whatever the balanced loads and unbalanced loads, the balanced loads, the phase currents are the same but differ in 120 degrees with each other. In unbalanced loads, the magnitude and phase will be not same, then it is called as unbalanced loads. And then the winding connections. Generally in three-phase winding has 6 terminals, that are A, B, C or R, Y, B at starting ends, and A dash, B dash, C dash are the finishing ends of the windings for three-phase system. So these interconnections are employed, these connections will be employed in the two types of forms. One is star connection and another one is delta connection. So what is star connection? Star connection means such similar ends, either it will be the start or either it will be the finishing or joined together at point N is called as star connection. So in this method of interconnection, the similar ends, that means at start ends of the three phase, that is A, B, C. That is starting ends of the three phase or finishing A dash, B dash, C dash, or R, Y, B, or dash, B dash, C dash, like that. Starting ends or finishing ends meet at one point, that is the neutral point, is nothing but the star connection. So when you take there is simple Y connection, star connection, the point N, whatever the point N is known as star point or it is called as neutral point. If these three phase voltage is applied across a balanced symmetrical load, the neutral wire carry three currents which are exactly equal in magnitude but are 120 degrees out of a phase with each other. Hence, these vector sum is 0. So, if suppose this star connection, if the three phase voltages must be same, whatever the voltage magnitude must be same and the phase angle will be 120 degrees each phase, out of each phase, then the neutral current, that is what is IR, what is IY and what is IB, when you add the three current, then you get the 0, then it is called as balanced system. If it be some neutral current is some value must be there, so there is some unbalanced system must be there. So when the three phases, when the vector sum will be 0, when you add the phase current of IR, when you add the phase current of IB, when you add the phase current of IY, then it comes to the 0, then it is called, then it is nothing but the balanced systems. So in this there is a star connection and delta connection must be there. So in this star connection means the starting ends or the finishing ends meet at one point is nothing but the star connection. So what is the basic relationship of the voltages? And that means voltages means there is line voltage and phase voltage, and line currents and phase currents in star connection. Line currents and phase currents in star connections. So here when you take the simple diagram here, that is ER, EY, EB will be the voltages, and lines line 1, line 2 and line 3, VRY, the voltage between the phases are VRY, VYB and VBR. The voltage induced in each winding is called phase voltage. Whatever the voltage induced in each winding, the windings ER, EY, Y, whatever the voltage induced in the winding, that is called phase voltage. And phase voltage and current in each winding is known as phase currents. So there are the phase voltage and the line voltage, phase currents and line currents must be there. So when the whatever the voltages or whatever the current induced in each winding is nothing but the phase voltage and phase current. The voltage induced in each winding is called phase voltage. The current induced in each winding is known as phase current. So line voltage VRY. So we have taken a simple diagram. So the vector diagram for phase voltage and current in a star connection is as shown in figure. Here ER is equal to EY is equal to EB, that is equal to phase EMF, phase EMF. So the voltage induced in the winding is nothing but the phase voltages. So ER, EY and EB is equal to phase voltages. Line voltages VRY between lines. VRY is in between the lines of line 1 and line 2. So what is the voltage of the vector difference of this line 1 and line 2? That is ER and EY. Like that, from line 2, that is equal to line voltage VYB. VYB is between the lines of 2 and 3. So the vector difference is EY and EB. Like that, line voltage VBR between the lines 3 and 1. So the vector difference is EB and ER. So we know that the 3 voltage, the 3 magnitude, that is whatever the phase voltage will be represent 120 degrees. ER, EY and EB will be 120 degrees, and the current will be IR, IY and IB, depend upon the load. So when there is the inductive load must be there, the current will be lagging position. And when you have to, already we have discussed, when there is the resistance point of view there, the both are in same phase. When there is the inductive point of view there, the voltage will be leading position. When there is the capacitive point of view there, there will be the current will be in the leading position. So there is the inductive loads, so the voltage will be in the leading position. So VRY, ER, EY, EB is the windings, the phase voltages, and VRY, VYB, VBR are the line voltages. So VRY is between the lines of line 1 and line 2. So the difference will be ER and EY. Like that, VYB between the lines 2 and line 3 is the vector difference of EY and EB. And VBR between the lines 3 and line 1 is the vector difference of EB and ER. So from this phasor diagram, so we have to represent what is the phasor. The potential difference of lines 1 and 2 is VRY is equal to ER minus EY. So generally when you observe this phasor diagram, ER, EY, ER, EY and EB. ER, EY and EB. So what is this? When you observe this, ER, so negative part it is minus ER, EB negative part it will be minus EB, and EY negative part will be in the minus EY. Other side it will be minus EY. So the 3 R will represent in the 120 degrees. So VRY minus VRY, VYB and VBR. VRY, VYB and VBR. So 3 phases must be 120 degrees phase difference. 120 degrees phase difference. So from this, when you observe here, VRY to VYB, how much it will be 120 degrees. Then VYB to VBR, it is 120 degrees difference. VBR to VRY, it is 120 degrees phase difference. Then these are the line voltages. So VRY is found between, with the lines of VRY is in between the lines of line 1 and line 2. So ER and EY, ER and EY. So reversed, EY reverse, and its value is given by the diagonal of the parallelogram in figure. Next thing, the angle between ER and EY reversed is 60 degrees. So total will be 120 degrees, and half part 120 from half part it will be 60 degrees, and then from that point it will be 2 parts, that is equal to 30 degrees and 30 degrees. So 60 degrees. If ER is equal to EY is equal to EB, that is equal to E phase, the phase EMF, then cos 30 is equal to VRY by 2 by E phase. Cos 30 is equal to VRY by 2. So here the angle will be 30 degrees. So cos 30 is equal to VRY by 2 by E phase. So from that, when you observe that VRY is equal to 2 into E phase into cos 30. 2 into E phase into cos 30. So 2 into E phase, what is cos 30? Root 3 by 2. That is equal to root 3 E phase. So the voltage in star connection In star connection, what is the relationship of line voltage and phase voltage is equal to line voltages are ERY, VYB and VBR. Phase voltages of ER, EY and EB. So line voltage is equal to √3 times the phase voltage. Line voltage is equal to √3 times the phase voltage. √3 times the phase voltage. But line current is equal to phase current. But line current is equal to phase current. Line current is equal to phase current because when the line current is IR, the phase current will be IR. It will be goes to the lineman. So it will be in the series part. So line current is equal to phase current, but line voltage is equal to √3 times the phase voltage. In star connection, line current is equal to phase current, but line voltage is equal to √3 times the phase voltages. Similarly, when VYB is equal to EY minus EB, this is vector, that is equal to √3 into V phase. Similarly, VBR is equal to EB minus ER, that is equal to √3 into E phase. So, but the VRY, VYB and VBR what voltages? It is line voltages. Hence, in star connection, line voltage is equal to √3 times the phase voltages. So, line voltages are, so we noted from the figure, line voltages are 120 degrees apart and line voltages are 30 degrees ahead with the respect to phase voltage. So, the angle between the line currents and the corresponding line voltage is 30 plus or minus 5 with the current lagging. So, in star connection, line current is equal to √3 into, line voltage is equal to √3 into phase voltage and line current is equal to phase currents. So, it's the same thing. In the last we discussed line voltages and phase voltages and phase currents. Now we discuss line currents and phase currents. So generally in current in line 1, that is equal to IR. Same thing current in line 2, that is equal to IY. Current in line 3, that is equal to IB. So since IR is equal to IY, that is equal to IB. IR equal to IY, that is equal to IB. So I phase is the phase current. So the line current is equal to phase current. Line current is equal to the phase current. In star connection, line current is equal to phase current. So in what is the in star connection, what is the phase voltage and phase line voltage? Phase voltage and line voltage means line voltage is equal to √3 times the phase voltage, but line current is equal to the phase currents. So what about the power? Generally, power is nothing but the voltage into current. In three-phase system, total power in the circuit is equal to sum of the three powers. The total powers in the circuit is equal to sum of the three-phase powers. Hence, total power is equal to 3 into phase power. So, what generally when you observed in the single phase system, V phase into I phase. In active power, that is equal to V phase, I phase, VL, IL cos phi, V into I into cos phi. Reactive power, V into I into sin phi. Apparent power, it is V into I. So, but here there is a three-phase system. So, we observe that 3 into phase voltage. So, power is equal to 3 into E phase into I phase into cos phi. But generally in star connection, line voltage is equal to √3 into phase voltage. So, phase voltage is equal to VL by √3. VL by √3. Line voltage by √3. But phase current is equal to line current. So, when you substitute phase voltage in this formula, P equal to 3 into VL by √3 into IL into cos phi. So, P is equal to √3 VL IL cos phi. P equal to √3 VL IL cos phi. This is the power in star connection. Same thing when you have to observe when you have observed, this is the active power. When you have observed the reactive power, root 3 into Q is equal to root 3 into VL IL side phi. When you observe the apparent power, root 3 into VL IL, root 3 into VL IL. So next one, that is the delta connection. So delta connection, or it is called as mesh connection. So here phase sequence R, Y, B. 3 phases must be there. R leads Y by 90 degrees and Y leads B by 90 degrees, and same thing, the voltages between the 1 and 2 is VRY. Between the voltages 1 and 2 are VRY. Like that, voltages between 2 and 3 lines, it is a VYB, and the voltages between the 1 and 3, it is VBR. So VRY leads VYB by 120 degrees. Like that, VYB leads VBR by 120 degrees. So VRY is equal to VYB, that is equal to VBR is equal to line voltage. Generally, I tell that when any voltage, it will be parallel to the number of any inductive loads, whatever it be, loads will be connected in parallel to the voltage must be same. So in the delta connection, so what is the generally delta connection? Delta connection means dissimilar ends will be connected, that is A B dash and B C dash and C A dash are connected to form a closed path, then it is called as delta connection. So in the delta connection, whatever the phases voltage must be there, that is equal to the line voltage. Phase voltage is equal to line voltage is nothing but the delta connection. Then VL is equal to E phase. VL is equal to V phase. So when you observe here, generally there is VRY, VYB and VBR. So the 3 phases must be a difference of 120 degrees.